All right, so hello everyone. Welcome back to your Comp 335 tutorial. This is your ninth tutorial. So if you've been keeping track, this is actually the before last week. So there's 2 weeks left in the course until we run out of material to teach you. So just keep that in mind for sort of study purposes and things like that. All right, so the content of today's tutorial is going to be quite straightforward. We're going to look at production simplifications. So looking at lambda productions, unit productions, and useless productions. And then we're going to look at the normal forms, Chomsky, and Grayback normal forms. All right, so let's get right into it. Production simplification. So the whole idea behind this section is you're given a grammar G, and this grammar has some undesirable productions. So one such undesirable production is a lambda production, which we're about to see. And the idea is for every such undesirable production, we want to convert G to an equivalent grammar G prime. And when I say equivalent, I mean that the language generated by G should be equal to the language generated by G prime. So we want this to hold, but we also want that G prime not to have those undesirable productions. So for instance, here, this A gives you lambda should be removed, okay? So that's the whole purpose of these production simplifications that we're going to see. And those are going to be used when we employ the conversion algorithm for Chomsky normal form. Okay, so I've talked about lambda production, so let's start with those. A lambda production is simply any production of the form I have a variable on the left and I have a lambda on the right. Okay, and then from this definition, we have a following definition of a nullable variable. A nullable variable is any variable such that A gives you lambda with 0 or more steps, right? So this means that if A gives you lambda, then A is nullable, right? It's a nullable variable. And if, for instance, B gives me A, then because I can do B gives me A, gives me lambda, B is also a nullable variable, right? So both of these would be nullable, okay? And so the idea is we're given a grammar G. This grammar must obviously not contain lambda, because if it does contain lambda, then it's impossible to remove all lambda productions. So we're given a grammar G such that the language generated by G does not contain lambda. Then we can always convert that grammar G to an equivalent grammar G prime that has no lambda productions and no nullable variables. And so how do we do this? We first need to identify all nullable variables. Then for each production rule, A gives you a bunch of different sort of variables and terminals. Add this production rule to your production set of production rules of G prime, right? So you obviously add all of the production rules from G, except, so essentially add all of the production rules from G, except something like A gives you lambda. So just don't add these production rules, okay? And then what you need to do is for each nullable variable and for each production rule that contains a nullable variable, you need to replace every possible combination of the nullable variables in your production rule, okay? So what does every possible combination look like? Well, to illustrate that, we're gonna look at an example. So suppose I have the following grammar G, right? And I want to get rid of all my lambda productions. So the first thing to do is I want to determine which variables are nullable. So I can immediately see that A is nullable and C is nullable. And from this production rule, I can also see that B is nullable. So the set of nullable variables is A, B, and C. Okay, so then the second step in converting my grammar that contains lambda productions to a grammar that doesn't contain lambda productions is copying and pasting all of the production rules except for the lambda productions. So in other words, my new grammar G prime is just going to be this taken off and then this taken off, right? And then what I want to do, so that's step 2. And then step 3 is for each production rule and for each nullable variables in those production rules, replace them such that you're producing all of the possible combinations of replacements for your variables. So what do I mean by that? Well, for instance, if I look at this production rule, A gives me BC, then what I could do with BC is I could replace B with lambda, right? So I could have lambda C, or I could have, I could replace C with lambda, so I could have B, I could have, sorry, yeah, so B and then lambda, let's say. So C is replaced by lambda. Here B is replaced by lambda. And I'm not going to replace all of my variables by lambda, right? Because then that would just give me lambda, lambda. So then I would end up with a production rule that just is a variable gives me lambda, but I'm trying to get rid of those. So I'm not going to include this one. And in general, you don't include a lambda production if you're trying to remove it, right? So then from the set of all possible replacements of BC with lambda, you get the additional production rules. A gives you B and A gives you C, right? Okay, so that's for A. For B, I'm not going to replace C by lambda because that would just give me lambda, so I don't want to do that. So then the last one is this guy where A, B, and C are all nullable variables. So that means I need to replace 2 variables with lambda, 1 variable with lambda, and also here all the variables with lambda since I'm going to get an A at the end, right? So I'm just doing all the possible combinations, much like how you would sort of count all the possible binary strings or something like that. Okay, so the first replacement I'm going to do, I'm just going to replace 1 variable. So let's say I replace A with lambda. So here this was A, instead I replace it with lambda, so I get BC. So just to make it clear, I'm not going to put the extra variable. So I have A, B, C. We actually move this as well. So I have A, B, C. So here I replaced for variable A. Then I have A, A, C. Here I replaced for variable B. I have A, A, B. Here I replace for C. Then I start replacing 2 variables. So let me replace A, B. So I have A, C. I'll also replace B, C. So I have A. So I'll just have B. And then let me replace B and C. So I'll just have A. Okay. And then I'll replace all of them by lambda. So then I'll just have A. Okay. And then so I'm done writing out all the possible combinations for all of the production rules. And so that this becomes my equivalent grammar G prime that does not have any lambda productions and by consequence, no nullable variables. Okay. So, you know, this isn't that, well, I don't think this is that difficult. I mean, if you have any questions, of course, let me know. And so to test that theory out, I'm going to make you try one. So I'll give you a minute and then we'll look at it together. All right, so let's look at this exercise together. So we were asked to eliminate all lambda productions. So remember, what are the steps? The first step is just to identify all nullable variables. So in this case, A gives me lambda, so A is a nullable variable, and B gives me lambda, so that's also a nullable variable. S isn't, because in either cases, so in either this case and this case, I have terminal strings, meaning that S itself can never give exactly lambda, right? So then I only need to really think of A and B, right? So what's the next step? The next step is to rewrite, to basically just copy paste the grammar without rewriting the lambda productions. So I have S gives me A, B, and S gives me A, B. And then I'm not gonna obviously write A gives me lambda, because that doesn't give me anything. And finally, I'll have B gives me BBA, right? So next, the next step is using the sort of nullable variables. Do this method that I showed, where you need to replace, you need to sort of list all possible replacements, right? So here for this production rule, A and B are both nullable, so they can both be replaced by lambda. So then the additional production rules that are going to result from that is, well, if I replace capital A by lambda, I'll get AB. If I replace the variable B by lambda, I'll get AA. And if I replace both by lambda, I'll just get A, right? So that's what's coming out of the replacement for AAB, okay? And then the same thing for this guy. In this case, you don't really have to list any combinations. There's just one. If you replace B by lambda, you just get A. All right. And then the last one here, B gives me BBA. Of course, A is a lambda, is a nullable variable. So then I can replace A by BB. Okay. So, so I guess this is step 2 and 3 together. And now I'm actually going to do an additional step, because you might notice that here I have the variable A a couple of times, but of course I no longer have the production rule A, right? So in this case, I'm going to sort of get ahead of myself and just remove these. This is going to be in the useless production rule section as well. But just to make the grammar a bit tidier, because A is never actually used, then I can actually already remove this production rule, this production rule, as well as this production rule. So then my final grammar, which I'll write in blue, is just going to be S gives me AB, S gives me A, S gives me AAB, S gives me AA, and B gives me BB, right? Okay. So then this is my final grammar, equivalent grammar G prime. Okay. And then it becomes a lot clearer actually to determine what L of G prime is here, right? So I'll leave that for you to look at, but you can kind of tell that it's a lot easier to determine what it is here than to determine what L of G is here. But if you do the same exercise here, then you should get that L of G is equal to L of G prime. All right. So any questions about this? No? Okay. So so in that case, let's go to the next.
I have a question, please.
Yes, yes. Yeah, go ahead.
About the examples that we've just solved.
Yeah.
Why don't we like replace the capital B variable with BB on the first line? Like we put S equals A, BB, or A, or A, B, B, or A.
Right. So you want to replace B by BB?
Yes.
Why would you want to do the only
Would it make a
replacement?
difference?
Well, yeah, I mean it's not gonna
But
change.
because we're gonna have like a more simple
Oh, you mean you want to
sort.
simplify it even more? That's what I'm I'm not quite sure what you're.
Regardless of what we're doing now, because I've seen like because B, capital B can only be BB, right?
Yeah. Oh, you mean yeah, sure, you can do that. Yeah. But I mean that's not the purpose of the exercise. But yeah, it would make a difference.
I understand it's not our what we're doing now, but we're simplifying anyway. And during like the lectures,
Yeah.
somebody asked the professor, and actually he didn't give like a clear answer. Okay, so I just wanted.
Yeah. Okay. Yeah, no, so I mean it's gonna be the next topic actually. But yeah, so you can replace B here. It'll give you the equivalent an equivalent grammar. Although actually maybe just to specify that's actually not part of simplification. So replacing B here by BB, that's not a step in the simplification. It's a step that you can use to help yourself in understanding what the grammar is, but it's not a simplification step. Because, so if I go to the next, so let me just explain what this step is, and then I'll show you why what you sort of, the replacement that you were describing doesn't fall into this. Okay, so so now we're going to look at unit productions, and then I'll also come back to that example in a second. So before removing unit productions, let's just define what a unit production is. So a unit production is any production of the form a variable on the left and then a variable on the right. So there has to be a single variable on the left and there has to be a single variable on the right. So given a grammar G, so we have a grammar G with unit productions, then we can always convert it to an equivalent grammar G prime without any unit productions. Okay, so how do we do this? With the following steps. So first of all, if you have any productions that look like A gives you A, you can immediately remove those, right? Because they don't really actually help at anything. The next step is you want to find all of the pairs of variables, the distinct pairs of variables, such that A can derive with 0 more steps, or in fact with 1 or more steps, B. Okay, so we're sort of extending unit production so that it's not just A gives you B, but A can derive the variable B. All right. The second, or I guess the third step is you want to take all of the, so imagine you have your grammar G prime, it has some production rules, right, which are not unit productions. So you have the production rules that are not unit productions. And so let's say union, you have the production rules that are unit productions. So then the idea is, so let's call this P1 and P2. So the idea is in G prime, you're going to simply copy paste P1 into G prime. Okay, so that's step 2 here. And then the next step is given all of the unit productions. So for instance here, let's say I have something like S gives me A. Okay, so then the idea is what I'm going to add to G prime. So let's say it's a union with P1 is I'm going to add S gives me all of the non-unit productions of A. So the non-unit productions of A. Okay. And then you repeat this step. So let's say you had, for instance, you also had B gives you in one or more steps, in one or more derivations C, then you would also have to add to G prime B gives you all of the non-unit productions of C, okay? And then in this way, if you do this for all of the unit productions and all of the derivable unit productions, let's call them, then you'll get an equivalent grammar G prime that has no unit productions, okay? So now if I go back here just quickly, this is not an example of doing that, right? Because here B gives you a terminal string, right? So this is not a unit production, so then it would not fall under this type of replacement, okay? All right, good. So this is in theory how the algorithm works. Now let's look at an example because it's normal that initially it's not maybe super clear. So suppose we have the following grammar G with a set of production rules given here, and we want to just eliminate all unit productions, right? So step 0 is removing A gives you A, so that's not anywhere here. Step 1 is then finding all sort of unit productions or derivable unit productions. So how do I do that? Well, I can see that S gives me A, S gives me C, so I can already use those. I also have that A gives me C, and I have that C gives me B. And so then by transitivity, I also have that S gives me in one or more steps B, and that A gives me in one or more steps B, right? So I have all of these guys, okay? And then the second step is just essentially copy all of the non-unit productions from G to G prime. So that's what I'm going to do. S is going to give me B, B, B. A is going to give me A and B, C. B is going to give me B. C is going to give me A, B, A, and C, C. And that's it, right? So now what I can do is I can add for each, so for each unit production, I can add the corresponding the corresponding non-unit productions from G prime. Okay, so here I know that S gives me A, so I'm going to add the production rules of A to S, so A and BC, right? Then I know that S gives me B, so I'm also going to add the production rules for B. Okay, it's poor choice of colors, but whatever. And then I know that S also gives me C, so I'm going to add the production rules of C. So A, B, A, and C, C. So this is for C. This is for, whoops. This is for B. Okay. There we go. B. And then this is for A. All right. And then I do the same thing for, I just do the same thing for all of the other variables, right? So for A, I know that A gives me, so now I'm not going to use colors just for the sake of time. I know that A gives me B and A gives me C, so I add B and A, B, A, C, C. And then here I know that B gives me C, or no, here B does not give me C. Just C gives me B, right? Yes. So C gives me B, so I'll add a B here, okay? And then, and this, so this is kind of like 2 and 3 at the same time. And this becomes your equivalent grammar without any unit productions, okay? So, okay, good. So let's see if this was understood by doing an exercise. So I'll give you again a minute to try it, and then we'll look at it together.
Sorry, we can't see the example.
All right. Yeah, sorry about that. I was, for some reason, I couldn't exit full screen for a second. All right. So yeah, that probably wasn't enough time, but hopefully you got some of it started. So now let's look at it together. So we have the following grammar that has unit productions, and the idea is to remove those unit productions. Okay. Well, the first step is again going to be ignored here. So it's to remove any production rules. A gives you A, so that's not here either. So we don't need to do that. Then I'm actually going to show you a trick for finding unit productions a bit more sort of systematically. So it's basically just using a graph. It's not that fancy of a trick. But basically, let's say here, you start with S, right? So I only create an edge to another vertex, which represents a variable, if there's a unit production, or if there's a unit production, and then you can look at the paths for the derivable unit productions. So here S, I know with a unit production can go to B, and it can also go to C. And here I'm actually quite lucky, there isn't anything else. But if, for instance, I had that C gives me A, then what I could say is I could also see quickly that S gives me A. Okay, but this is just for the sake of illustration. In this case, I just have S gives me C and S gives me B. Okay. So then from here, I can. So the second step is to basically copy all of the non-unit productions, right? So I'm just going to do it on the example itself. Here, I'm basically just going to have all of the non-unit productions in the new grammar G prime. Then I'm going to copy all of the non-unit productions from B and C, right? So from B, I have AA, right? So B gives me AA, so I'm going to copy that one. So this is from B. And then the one from C is CCD. So that's the one from C, okay? And then this, right? And so that's about it, right? Because I don't have any more sort of derivable unit productions. So then this would be an equivalent grammar G prime without any unit productions. Okay, any questions about this?
So as opposed to the Lambda productions, in this one, we don't remove the productions. Once we, well, yeah, it wouldn't make sense to remove the productions once we remove the units.
Yeah, that's right.
Because for the Lambda production, we just remove them. In this case,
we replace them. So like here, instead of S gives you B, you're replacing that with S gives you all of what B gives you, basically.
Yeah. So even if we don't find any other use, yeah, it's fine. Okay, thanks.
Okay. All right. But just FYI, actually, like when you actually we'll do an example at the end, but when you actually do all of the simplification, you start by removing all lambda productions. So this was just for the sake of an example, but normally there wouldn't be any lambda productions at this stage. Okay. It was just to keep the example short. All right. So now the last topic, or sort of the last simplification, is useless production rules and useless variables. So here there's a couple of definitions. So if we're given a grammar G and a variable A, we say that the variable a is useful if it appears in the derivation of at least one string w. So when I mean a string w, I mean a string of terminals. So that is if at any point in time I can start with s, and then I can sort of do some derivations, and then at some point I have an a. There could be strings here and strings here, right? But if I use a production rule from a, and this leads to a set, a string w, which is just a string of terminals, then a is considered useful. Otherwise, so if that never happens, if there are no such strings, if there are no such string of terminals where a variable a can be used in the production rule, then it is considered useless. Okay. So that either means that the variable is unreachable. So starting from s, let's say s is here, I can maybe never get to the variable, let's say c, okay? Or it's non-generating, meaning that, for instance, I have c gives me cc and only that. So then whenever you get to c, you're kind of trapped, and you can never get out of you can never at the end replace your last c with a terminal. So that's what we mean by non-generating. Okay, and then another sort of analogous definition is for a production rule. So production rule x gives you y is useless if it does contain a useless variable. Okay, and then so clearly, because they're useless, removing useless productions does not remove anything from your grammar G. So then if you remove production rules, useless production rules from G, you get an equivalent grammar G prime. And then a good practice is to start by eliminating non-generating variables first, and then non-reachable ones next. All right. So so to illustrate this, let's look at an example. So I have the following grammar G, and I want to remove all useless productions, right? So I want to remove all non-generating productions first. So what are the non-generating productions? Well, to sort of look at this, to determine this quickly, you can check if each of your variables points to a terminal or points to a variable that can lead to a terminal. Okay, so for instance, what I mean by that is, for instance, here A is generating because you can replace A by lambda. Okay, B is also generating because you can replace B by BA, and then A by lambda. So then you can get B gives you B. Okay, and S is also generating because you can replace S by A and then A by lambda. Okay. However, C is not a generating a variable, because here, let's say you end up replacing C by ACA, then you're still stuck with the variable C, right? And then again, if you replace C again by ACA, you'll just get AACAA, right? And then you're going to keep replacing C with C's, but you're never going to get rid of this variable C, okay? So that means that C is non-generating, which means that I can remove from this grammar all of the production rules that use C. So I can remove this, and I can remove this, okay? So that's for non-generating. Then for reachability, I can use a similar trick with a kind of sort of transition graph, where I create an edge if and only if I can get from, let's say, variable S, let's say from one variable to another. So from S, I can get to A with this production rule. From A, I can get to myself, so that's not very interesting. And then from B, From B, I can get to A, but there is no way for me to go from S to B, right? Because there just isn't a production rule for that. And so that means that B is unreachable, because from your start variable S, you can never get to B. So what that means is that I can also eliminate the production rules with B. So I can remove this one, and that's about it, right? So then the simplified grammar is just going to be this guy. Okay, so that's removing useless productions. So then let's look at another example. Here, I think this is actually, this might be the same one as before. And so I'll give you, say, a minute, or yeah, sure, a minute to try this one. And we'll look at it also together. All right, so hopefully you had some time to look at it. So here we were asked, given a grammar which contains useless productions, to remove all the useless productions. So what did we say? We said first we wanted to remove non-generating productions. So how do we do that? So, well, here clearly S is generating, because I can just have S gives me A, so this one's okay. This one's okay. Then A can be replaced by lambda, so that's fine. B is replaced by AA, and then A can be replaced by lambda, so this is also okay. D can be replaced by D cubed, so that's fine. But here C, we have the issue where it's a very similar issue as before, where if you end up in C, then you can never get rid of the variable C in this production rule. Okay, so for instance here, if I replace C by its own production rule, then I would just have C, D, D again, right? And then I could never actually get rid of this C. For as long as I tried, I would never be able to get a terminal string. Okay, so what that means that I can remove all the production rules that contain C. So for instance, I can take this one out, and this one out. Okay. And then the other step is to remove unreachable variables. So I'll do the same thing. I'll create a graph. If I start at S, I can go to A, and I can go to B with this guy and this guy. So then from A, I can go to B. From B, I can go to A. And here from D, I can't get to D, right? And so what that means is D is unreachable. Okay, so that means that I can also remove D. So what that means is that when you simplify this, removing useless productions, you're left with this grammar. Okay, so there's a question on slide 12, if we were to remove unit productions. So, well, actually, maybe let me just quickly ask before I answer that. Are there any questions about this? Because if no, I can answer that question. No? Okay. So if you wanted to remove unit productions, From the, well, let's do this grammar because the top one would be a bit longer to explain. Then let's just assume we're not getting rid of lambda productions for now. So here we just have A gives you AA and lambda. And here, let's just say we have S gives you nothing for now, even though this isn't very valid syntax, right? But this would be in, like, let's say step 2, where you're rewriting everything without a unit production, right? So this is where you would be. Then you would have to add all of the non-unit productions of A, right? So then you would have AA and lambda. And that would be your equivalent grammar without unit productions. Okay. You can further reduce it, but so when I say simplify, I specifically mean removing lambda, removing unit, and removing useless, right? But you can definitely, like, clearly here, there's a lot of useless things that are, no pun intended, but there are a lot of useless things that are happening here, right? You clearly don't need to do S gives you AA and then go to A and then, right? Because here the language is clearly A star, right? So you could just, then you could just say, oh, it's just S gives you AS or lambda. That's fine, yes. But if we want to be strictly like simplification, then this should be your final answer. Okay, you shouldn't, and I'm mostly saying that in terms of like what's expected maybe in a question for a test or something. Try not to sort of over reduce it because this is enough. Yeah. Okay. So so now that we've looked at the 3 grammar simplifications, how do these sort of work together? Well, if we want to sort of simplify a whole grammar, then the steps are first remove all nullable variables in lambda productions, then remove all unit productions, and then remove useless productions. And so the order is very important to remember, okay? Because if you don't respect the order, then you might have to sort of redo a step. And so it's not the efficient way of doing it. And if you just do it in one pass, then you might not get a simplified grammar, okay? And so to see if this was well understood, this exercise asks you to simplify it completely, right? So it asks you to basically remove lambda productions, then to remove unit productions, and then useless productions. So I'll give you a bit longer for this one. Let me give you 2 minutes to start it off, and then we'll look at it together. Alrighty, so hopefully you had some time to start this exercise off. So there are a couple of steps here. So of course, remember you needed to respect the order that I sort of just wrote here. Trying to think of the best way to, yeah. I'm actually going to move this here. Okay. All right. So I wanted to first remove lambda productions and nullable variables, right? So to do that, I needed to identify the lambda productions and nullable variables. So what are they? Well, I can clearly see from this guy and this guy that there's A and D. Oops, not B. There's A and D. And then I also know that B gives me D. So then B is nullable, and C gives me B. So C is nullable, right? Okay. So then A, B, C, and D, but not S, are nullable variables, right? So now I'm going to do this replacement of all combinations, but first I need to copy all of the non lambda productions. So let me do that. So A, B gives me B. So notice I didn't rewrite A gives me lambda, of course. C gives me B, and D gives me BDA. All right. Now, basically, I need to do this trick for like this trick of replacing all combinations for all the production rules, because everything except S is a lambda production. So then let's do that. So for AAA, I can replace A by lambda, so I can get AA. Then for ABB, I can replace 1B by lambda, so 1B by lambda, or 2B's by lambda, right? And then for DAB or DAB, I can replace the D by lambda, so AB, the B by lambda, so DA, or both the D and the B by lambda, so just A. Okay, and here I'm going to get some overlap. So let me just remove the overlap. So there's AB is there twice, and A is there twice, and I think that's it. Yeah. Okay. Okay, good. So that's for S. Then for A, I'm going to replace the A on the left by lambda, the A on the right by lambda, and then both A's by lambda. And then here, I'm not going to replace D by lambda. I'm just going to replace B by lambda to get B. Here, of course, I'm not going to do this, right? Because that would introduce a lambda production. So I don't do anything there. And then for D, I replace the variable D with lambda, so I get BA. Okay, so then the grammar, the equivalent grammar without lambda productions is this one, right? So this guy. Okay, so let me just clean this up so I can copy it. So okay, so I have this guy. Now I want to remove unit production. So let me just move this here. And copy this. So I think, come on. Okay, it doesn't want to copy. All right, let's just say I'm going to move it, okay? But imagine it got copied, right? So now, actually, I think my OneNote is lagging. That's probably why. Yeah. Come on. Okay, let me just close it. Okay, yeah, let me just close it quickly. All right, is it working now? Yeah. Okay. So now I'm gonna just share it because I know as soon as I said, is it working now? Someone was gonna say, oh, we can't see your screen. All right, share, all right. Okay, good, okay, excellent. So, so now I wanna remove unit productions, right? So, so how do I do that? Well, I need to look at the unit productions that exist in my grammar. So what are they? Well, I have B gives me D, right? So I have B gives me D as a unit production. Then I have C gives me B, and then by transitivity, I have C gives me D as well, right? And I think, yeah, and that's it. Okay, so then to remove unit productions, I just need to copy all of the non-unit productions. So in this case, because copying is dangerous, I'm going to just remove the unit productions from this grammar. And then I'm going to add the non-unit productions of each of the variables, right? So, so in this case for B, B gives me D. So I'm going to add the one for D. So BDA and BA, right? And then for C, C gives me B and D. But in this case, because I already wrote B, I wrote the D part for B, I can just write, I can just copy B, right? Because this part is D, right? So there's no need to recopy the same production rules. So I can just write this. Okay. Right, so that's removing unit production. And then the last thing is removing useless productions. So I haven't been very, I haven't asked any questions. So this is going to be the first one. So what are the, if there are there any non-generating variables? Silence means no. Okay, yes. So silence is good. And also to heart, it's good. So no, there are no non-generating variables because in each case, so for instance, S can give me A can give me A, B can give me BA, C can give me BA, and D can give me BA, right? So they're all generated. What about unreachable? So if I draw my graph, right, S gives me what? I can reach A, B, and D from S. And then from A, I can only reach A. From B, I can reach myself and D. From C, I can reach B and D. And then from D, I can reach myself. Okay, and so what you can notice is that, yes, as someone said, from S, I can never reach C, meaning that C is unreachable. So then I can just remove all of the productions that have C. So I can remove this. And that's all I can remove. So then the simplified and final grammar is this guy. Or if you want to make it sort of, you want to look at it in a nicer format, it's this guy, right? So, so then this would be your simplified grammar. And so what I'd like you to notice is that simplified does not equal less productions, as you can clearly see, right? So the number of productions has increased. Okay. So so that's something to keep in mind. All right. So any questions about grammar simplification? Could you show? Yes. Yes. There you go. So,
Sorry, how
yes.
did you get from B? How did you get the B? Like you have B goes to BB or B. How did you get just the B again?
Just the B.
Yeah, the small b when you go from B to BB, or you go to the small b.
It's because B was nullable. So, like in my first step, which sucks that I didn't copy, but here in my first step here I had BB, right? But B was also nullable because why is B nullable? Because B gives me D and then D gives me lambda, right? So I can, through 0 more steps, get to lambda with B, right? So then here I can replace this lambda, this nullable variable, which is lambda, so I can just have B. So that's how you introduce the extra terminal. Is that clear?
Thank you.
Yeah, no problem. All right. So if there are no questions about if there aren't any other questions about this, geez, I can't speak today. Then I'll move on to normal forms. Okay. So normal forms, what are they? So there are two important types of normal forms. There's a Chomsky normal form, which I always like to note that Chomsky is named after a very famous linguist, Noam Chomsky, who's actually still alive, which he's like 90 something. And so I think it's very cool that there's a theorem, or in this case, a definition named after someone who's still alive, which doesn't really, happen very often in mathematics. Things like, Euler and Gauss's theorems. These are people that existed 200 years ago, but Chomsky is still alive, or at least last I checked. So normal forms, why are they useful? So Chomsky normal form is actually quite useful because you might have seen this in the lecture, but it's a good way of taking a context-free grammar and then sort of converting it to CNF so that the parsing of the grammar is a bit faster. So if I remember correctly, it's not that much faster, so it's still something like n cubed. But it does allow for some additional efficiency. So that's the whole reason why there are normal forms. It's for things like that. So it's very similar to how, like if you took the database class, there's normal forms for databases. This is kind of an analogous sort of concept, but for context-free grammars. So that's the motivation. So now, what is Chomsky normal form? So we say that a context-free grammar is in Chomsky normal form or in CNF if all of the productions look like a single variable on the left and then exactly two variables on the right, or a single variable on the left and then a single terminal on the right. Okay, so each of the production rules have to look like this. Okay, so meaning that something like this is not in Chomsky normal form because, for instance, here I have the variable s gives me the variable a. This does not look like either this guy or this guy, so already it's not in CNF. If maybe, for instance, I had, let's say, AA, then this would still be no bueno because here I have a, the variable a gives me the terminal AA. So then what if I had AA instead of just the terminals AA? Then again, it still wouldn't be good because here I have a terminal and then three variables. So I would need to sort of change this. And so one way to sort of change this particular production rule is, for instance, let's just say, for the sake of argument, that you had A gives you A. So then you had A, B. Then the trick is essentially to take your variable A and then just add as sort of a temporary variable, an extra variable V1. So let's say V1 points to AAB, or sorry, AAB. But then this is still not in CNF, so then we just do the same thing. We replace AB by V2, and then V2 points to AB. So then this with, let's say, this, sorry, let's use blue, is in, so this is in CNF, okay? And so what I just showed you is the typical conversion algorithm of something that's not in CNF to something that is in CNF. But let's actually look at the algorithm more rigorously. So, so any context-free grammar where lambda is not in the language generated by G. So of course, why is this very important to check, right? Because the first step in converting a CFG to CNF is to simplify a G. And if you remember from removing lambda productions, if you remove lambda productions and lambda is in the language generated by G, then removing lambda productions is going to remove lambda from the language generated by G. So you should always check before you start the conversion algorithm that lambda is not in L of G. If it is, then remove lambda in your conversion step. So maybe let me write, if lambda is in L of G, remove it in your simplification, and add it back at the end. So what that'll mean is that you won't have a grammar which is exactly CNF, but almost, right? The only thing that won't make it CNF is the lambda production. Okay. So so then, as I was saying, so you have a grammar G and you want to convert it to a CNF, to an equivalent grammar in CNF G prime. So then the first step is to simplify the grammar G with the steps that I showed before. And then for each terminal, so for instance, if the set of terminals was AB, for each of those terminals, create a variable TA gives you A and TB gives you B. Then add that to the production rules of G prime. Okay. And then make sure to replace, so this isn't actually written, but replace all terminals X in your production rules P with TX. So what I mean by that is, suppose you had S gives you A, B, B, then you need to create TA gives you A and TB gives you B, and then replace A by TA and replace B by TB. Okay. So you do that for all of the production rules and then for all of the terminals. And then the last step is for all of your productions that look like, so by this step, because you've done this exercise, then all of your productions either look like A gives you a terminal, or A gives you a bunch of variables. So let's say n variables. And so in that case, what you can do is the trick that I showed before. So let's say you have C1, C2, ... Cn, then replace C2 to Cn by, let's say, V1. Then V1 becomes C2 to Cn. So then replace C3 to Cn by V2. V2 becomes that. and so on until you have Vn minus 2 gives you Cn minus 1 Cn. Okay, and so then this production rule is converted to these production rules respecting Chomsky normal form. Okay, so that's how the algorithm works. Let's look at, okay, so let's do an exercise. So here you have this grammar, this context-free grammar. So in theory, you should simplify it, but for the purposes of times, I simplify for the purpose of time. For the purposes of time, oh, I got it right. I simplified it for you, but maybe one thing to note here is that if this is G, lambda is in fact in L of G here, because here S gives you A and then A gives you lambda. So then what I write here is that in your simplification step, you remove this lambda and then make sure to add it back at the end. Okay, so that's what we're going to do. So here I simplified it, I remove unit productions, I remove useless productions. And so now this grammar in blue is the one for which we need to apply the Chomsky normal form conversion algorithm. So let me zoom in on it. So this is the grammar. So I'll give you a minute to convert this to CNF, and then we'll look at it together. Okay, so it's already been a minute. So let's do the conversion.
We can't hear you, sir.
Thank you. All right. That had to happen at least once during the semester. So, okay, let me go back. Right. So we have this grammar in blue, and we want to convert it to CNF. So what we first need to do is create terminal variables. So TB gives me B, and TA gives me A, right? But then I replace all of the terminals by those variables. So TB, TA, TB. So I'm very lazy and I'm just doing it here. Right, so I have this. Okay. Then the next step is, actually, I made a mistake. I'm not going to replace this terminal and this terminal. because then I would get a production rule S gives me TB, where this is a variable, and then that wouldn't respect Chomsky normal form. So I don't replace that guy. So I keep these terminals, but the rest is okay. And in this case, these two production rules are the only ones that don't respect CNF. And luckily, they're actually the same. So I can actually reuse my variable. So I'm just going to say V1 is TATB. V1 is TATB. We'll remove this and move this up. So then, okay, good. So then V1 is TATB. Then I can replace TATB with TAV1. And the same thing here, I can replace TATB with V1. And then this becomes my equivalent CNF. Okay, any questions for this? Oh, and then of course, the last step here, if we want to keep the grammar equivalent, is I would add an additional production rule, S gives me lambda. But then this is no longer in CNF, but it's there, so it's there to keep G prime, to keep this from being true. All right. So any questions about CNF conversion? No? Okay. It's pretty straightforward. The last thing we're going to talk about very quickly, and then I'll let you go, is Grayback normal form. So we're not going to look at sort of proofs and conversion algorithms for Grayback normal form. It's just good to know that it exists. So if you have a context-free grammar G, it is said to be in Grayback normal form if all of the production rules look like a single variable on the left, a single terminal at the leftmost part of the right-hand side, and then a bunch, 0 or more variables after the terminal. So something like S gives you AB, SBS. This does not respect Grayback normal form because you have terminals here. But then if this was a variable, then this would be okay. This would be okay, right? Because X can be just lambda here. It could be no variables. So then this would be the only thing that wouldn't respect it. So then let's say this was A instead. Then this grammar, this modified grammar would be in GNF. Okay. And so we have a theorem here, which says that, so very similar to the theorem for CNF, that every CFG such that lambda is not in L of G. So again, using the same trick as before, sort of applies. So every CFG where G does not generate lambda can be converted to an equivalent grammar G prime in GNF. Okay. And so one last thing I'll say is that you don't need to sort of, for this guy, you don't need to know the proof, right? But it's very useful, right? It's very useful to know that this is true, okay? Because you can have grammars where you do have a proof for those grammars, and you could maybe use this theorem in your proof. Just saying, okay? And that concludes this tutorial, right? So, oops, dropped my pen. So if you want to leave, you're free to go. But if you have questions, and actually I have assignment 3 out. So if you have questions about assignment 3 in particular.
Hello, sir.
Yeah.
Yeah, I have a question
Yeah.
for assignment 3. Actually, the last question, assignment 3. It's about context-free languages. And it's asking us to basically demonstrate the grammar, provide the grammar if it is indeed context-free.
Yeah.
My question is there some kind of procedure or protocol to identify whether or not a given language is context-free? What kind of rules should we follow, or what kind of logic should we follow?
There is, there's a pumping lemma for context-free grammars, for context-free languages.
Okay.
Which, when are you going to see that? So actually, you might not see that tonight. So then, yeah, so there is, but then I don't know if you'll have time to look at it. But my advice maybe for that is there are some known languages which we know aren't context free, which you'll see later. So for instance, something like AN, BN, CN. This is not a context free language. And so the reason for that is maybe a bit, it's a bit difficult to explain without using the pumping lemma, or even without using kind of a stack, because I don't think you guys saw push down automata either. So because for instance, let me just, if we look at ANBN, right? The idea behind the context-free grammar here is S gives me ASB or lambda, right? So this is the context-free grammar. The machine, so if you wanted to write a machine for this, the idea would be what? It would be to use something like a stack, okay? So you would need to use a stack where for each A that you read, you push an A, right? So let's say you push n A's. So you have n A's in your stack, and then you read, you need to read the same number of A's for your B's, right? So then for each B that you read, you have to pop an A, okay? So then you can do this for this language. And so you'll see tonight probably that if you can create a pushdown automata, then it also means that it's context free, okay? So then if something is not context free, the intuition is that sort of one stack is not enough. That's the intuition I can kind of give you. So for instance, here, it's not enough because I push NAs, let's say. So I push NAs, right? Then I pop NAs for the Bs, but then I've sort of lost track of the number N for my Cs, okay? So then I need actually more than just a stack. I need something like 2 stacks. So if I had 2 stacks where I could push A's, then pop B's, and then at the same time push B's, and then pop B's, then that would be enough to sort of accept the language. But that's not 1 stack, that's 2 stacks. So a push down automata isn't as powerful as that. So that's maybe the intuition I can give you, is that you kind of need, you like with context-free grammars, you have some memory that's allocated to you, but the memory is very basic. It's just a single stack, okay?
Okay.
And yeah.
And for question 3, are we supposed to provide some kind of proof that explains? I know that there is Chomsky normal form, another one. There's a second one.
Yes.
Are we supposed to provide some kind of proof that explains like the functioning of one of the 2 forms? Or because I'm kind of confused, like what kind of answer they're looking for? If you could just give me an idea.
The answer is a.
Do they want an explanation or like a proof?
So this is asking for a proof. It's asking that if you. So what's the question asking? It's asking, suppose you have a context-free grammar G. Then show that you can always convert G to G prime such that the production rules in G prime are this.
Okay.
That's what it's asking for.
Okay. Thank you.
Yeah, no problem. Okay, good. Any other questions about the assignment or anything else? So in general, I mean, this question, we just did it, right? I mean, we didn't just do this exercise, but we did something similar in the tutorial. This is pumping lemma proofs. So just, again, I'm going to remind you, don't pick a specific m. So don't set m equals to 7. Don't do that. M has to be still arbitrary. Yeah, and so for this, I kind of, with the stack answer, I think that should help a bit. So yeah.
Excuse me, is it okay if you ask questions on the homework right now?
Yeah, that's why it's out. If you want to ask a question.
I had a question about the pumping lemma for the number one. First question first, like number one. You say don't choose m equal to a fixed number, but is it okay if, because in the case of this one, if we just prove that an bn is not regular, we can put vk, the k, we can put that to 0. We don't have to put that to an m.
I mean, k can start from 0.
Okay, but if we say like b0 a m bm, is that doable, or is that
I'm not going to answer if it's doable, but I mean, k can be 0 here.
Okay.
Right.
Okay.
Any other questions? No? Okay. Well, so in that case, right, so your assignment is due Wednesday, so don't forget about that. So next tutorial is going to be about PDAs, so push down automata, and yeah, so that's about it. So again, let us know if you have any other questions, and I will see you Wednesday.
Thank you. Have a good day.
Thanks.